Okay, why don't we get started then? Professor Durgan is out of town. My name is Peterson. My office is upstairs next door to Professor Durgan's office if you need to get a hold of me for anything after class today. As I understand it, you have been talking about electrostatics, and we'll continue with that discussion today here. I'd like to start just by summarizing some of the various equations in that of electrostatic fields. And then we'll take those equations and do some things with them. So up until now we've talked about, or you've talked about, I guess, some of these equations, and one of these equations is an equation that says the integral of E dot dl around a closed path equals 0, or that E is a conservative vector, or you may have talked about that in a couple of different contexts. I think you did some line integrals last time in here. And there's another equation that says the integral of d dot ds over a closed surface, and really it's any closed surface, is equal to the charge enclosed by that surface. Okay. So those are the two integral relationships that involve the electric field or the electric flux density here, D and E. There's also two equations in differential form that involve these fields. There's one equation that says that E is minus the gradient of V, and there's another equation that says divergence of D is equal to the volume charge density. I'll call that rho sub V here. And as we go on, over the weeks ahead, we'll see how these equations are related to each other and generalize them slightly into the final forms of what we call Maxwell's equations today. Okay. If we're in different kinds of materials, we have other conditions that come into play. If we're in conducting materials, our field has to be 0, so we have both the electric field equal to 0 and the electric flux density equal to 0. Whereas if we're in a dielectric material, which is a plastic, ceramic, wood, something like that, then we have a relationship between D and E, where D is proportional to E, and the constant of proportionality is what we call the permittivity of the medium here. So those are the basic equations that we have here. Now we can play around with various quantities. Charges produce force fields around them. We can define a voltage around a charge. We can define an electric field around a charge. We can define a electric flux density D around a charge. And then we can show how these different things are related. So for instance, we can calculate the voltage from E by a line integral. So we'd have V given by the integral of E dot dl between 2 points. So if we have a charge density, that produces a field, and then we can integrate over that field. We can integrate over the E field to get the voltage. This equation says we can differentiate the voltage to get the E field back again. So we can cook up problems where given one of these functions of position, we can find the other functions of position, and so on. So there was a question about a line source or a surface charge or something like that. I don't know that it makes too much difference what the charge distribution is, but if you have a distribution of charge, charge density or something, then that will produce all of these fields. All right, so we'll get a voltage, we'll get an electric field, we'll get a D field, and then they will be related by the various equations involved here. So for instance, if we had let's say we had an infinite line charge, there's an electric field produced by that. If this is a charge density rho sub L coulombs per meter or something, then you'll get an electric field produced by that, which will basically be pointing away from the line charge, and it'll have a value rho sub L divided by 2 pi epsilon 0 rho in the rho hat direction. So you could look down on the line charge, and you'd look at this electric field. It would be pointing out away from that charge, sort of symmetrically distributed, and it would decay as you go away from it. If you wanted to calculate the difference in the voltage between 2 points, you'd have VA minus VB being the integral from A to B of E dot dl. And you could do the integration. If we were just integrating in the rho direction, we'd be doing this integral over rho. I may have the sign wrong on that. I haven't reviewed this in a while. Now, there was a question about that. Is that getting to the question?
Actually, I was having difficulty in doing the homework. I would get the electric field due to some orientation, and I just could not take it from the electric field to being a voltage.
Okay.
And I was wondering if you could just provide an example of one situation.
Well, the kind of situation you'd have if you've got the electric field as a full function of position, to get the voltage you would have to do a line integral like this. You would have to define a particular path to integrate it over and integrate it along that path. So I don't have an example right in front of me here that I can follow, and I don't know what the exact problem was you're assigned, but does anybody have the problem?
Can I give you an example? Like, if I had a point charge inside of a sphere,
okay,
a conductor sphere, and I wanted to know the the potential of a point outside of that sphere.
Okay. So you've got a point charge, Q, say, centered inside a sphere.
Yes.
All right. And now you're going to, you're wanting to know what the voltage is at some point out here.
Yes, sir. Yes.
And what's your voltage reference here? Is there a point where you know the voltage is 0, or?
Out at infinity, that's the only thing I can imagine.
Okay. So if you have a point charge Q, you're going to have an electric field that's basically given by Q over 4 pi epsilon r squared in the r direction. Is that consistent with what you're doing here? So if you want to know the voltage at some point, then you're basically going to integrate from that point, say r, to infinity, and that's your reference. So the voltage at infinity is 0, the voltage at r is something else, and then you're integrating basically this function along a straight line, and you'd be dotting that with a differential length, basically r hat dr, along that straight line. So the r dot r goes away, you got some constants in here, you've got an integral of dr over r squared to integrate. That's going to give you, that's r to the minus 2, so you're going to integrate that, you're going to get something over r. So basically, if you take all the constants into account, this is going to give you something over r here. You evaluate it over the limits of integration, you're going to get something over r out. So that's I think that's what you're describing. Does that make sense to anybody here? So does that help with setting this up, or is that?
It does. If the sphere were a conducting sphere, would that matter? Would that change the situation?
Well, if you're putting a charge in there, if there isn't a neutral amount of charge in there, if there's a net charge of Q centered at the middle of that sphere, that doesn't really change anything. Then you still have this field outside. I think that's if that's the way the problem is set up. I don't know if that's the way.
Well, for the specific problem, it had a volume charge inside.
Okay.
And I was just trying to think of it as a point charge at the center.
Right. Well, if the volume charge was spherically symmetric and you integrated over it and got a total of Q coulombs or something, then it would be the same as a point charge Q at the origin. The field inside the sphere would be different, but once you get outside of that region, you would have basically this same expression for the field.
Okay, that helps. Yes, thank you.
Okay. Okay, so let me go back then to these equations, and what I'd like to do is to observe that we could combine some of these equations together here. So for instance, we can take the differential form of Gauss's law, which is this last equation. We can substitute in the constraint about dielectric material to that, so that we could write this as a divergence of, instead of D, we could write that as epsilon E is equal to rho V. All right, epsilon being epsilon 0, epsilon r, both together here. And then we could take the first equation that says E is minus the gradient of V, substitute that in for E, and then this becomes divergence of epsilon grad V with a minus sign is equal to rho V. Okay. So this is what is really a general form of what we call Poisson's equation. And that's used, for instance, if you wanted to find the voltage, in this case, potential, due to some distribution of charge. One application of this is in modeling the fields around p-n junction semiconductors or something, where you've doped it with a certain charge profile that's fixed, and you want to know the fields around that. If epsilon is not a function of position, then you can pull it out of the derivative. It's just a constant then, and you can write this as divergence of the gradient of V is equal to minus rho V over epsilon. And this divergence of the gradient of V, if you work that out, divergence is the x derivative of the x component of the gradient of V. The gradient has an x component that's basically dv dx. The divergence says take the x derivative of the x component, the y derivative of the y component, the z derivative of the z component, and the x component of the gradient is dv dx, the x component, the y component rather, of the gradient is dv dy, the z component of the gradient is dv dz. So this becomes second derivative of v with respect to x, second derivative of v with respect to y, second derivative of v with respect to z. And this is what's called the scalar Laplacian operator. So you may have encountered that before in a differential equations class or somewhere. And we normally denote this operator with the notation del squared. So it's really it's a shorthand way of just writing divergence of the gradient. here. Now, the gradient takes a scalar quantity and gives you back a vector. The divergence takes a vector quantity, gives you back a scalar. You put those two together. Here we're starting with a scalar quantity, we're getting back a scalar. So this operation is a second order derivative that starts with a scalar, gives us back a scalar. You don't have to know anything about the intermediate vector quantity that pops out of this. Okay. So if we go back to this equation then, this gives us sort of the ordinary form of Poisson's equation, which is del squared V is minus rho V over epsilon. And if you have no charge in a region, then the right-hand side goes to 0, and this becomes del squared V equals 0. And this is what we call Laplace's equation. So the scalar potential voltage function that we're talking about here, associated with some charge distribution, is either going to satisfy Poisson's equation, or if there is no volume charge spread around in some region, it'll satisfy Laplace's equation. Okay. So those are standard differential equations that you might encounter in other disciplines and so on. They show up in equations involving things like heat transfer and all that.
Does this also apply to surface charge density and line charge density?
Yeah, all of this applies whether you have any distribution of charge creating some kind of field around it. So if there's a field there, there's a voltage distribution there, then these equations are going to apply to that situation. Okay. Now this is the form of the scalar Laplacian in Cartesian coordinates. If you're doing a problem with line charges, for instance, you may find it more convenient to work in cylindrical coordinates. And in cylindrical coordinates, we can write down the Laplacian directly. And that's given by del squared V 1 over rho, derivative with respect to rho of rho dv d rho, 1 over rho squared, second derivative of v with respect to v squared, and the z component doesn't change. So this is just a complicated way of sort of stretching the coordinates to get from Cartesian to cylindrical. If you're interested in problems with spherical symmetry, it might be more convenient to work directly with it in spherical coordinates. And then you'd have 1 over r squared ddr of r squared dv dr plus 1 over r squared sine theta, derivative with respect to theta of sine theta dv d theta, plus 1 over r squared sine squared theta of second derivative of v with respect to phi squared. So these are normally not formulas you try to remember. You would look these up on the inside cover of your textbook or wherever you happen to have them jotted down if you need them. But they just give you the direct way of computing this in this cylindrical and spherical coordinate system. Okay. All right, so as an example, suppose we're given a voltage in some region as a function of Cartesian variables here, x, y, and z. And the thing about voltage is that in terms of the fields and forces and so on associated with voltage, you can always offset voltage by a constant. So you can always add a constant everywhere, and that doesn't change anything since the field depends on the derivative of the voltage. So let's say we had some constant in here that I'm not even going to specify, minus, say, a voltage V0 XYZ. Okay. So my first question is, does this satisfy Laplace's equation? All right. If it doesn't satisfy Laplace's equation, then it's probably not a valid voltage for this problem. Okay. So we can substitute this in. We want to calculate del squared V. So we take a second derivative with respect to x of V here. And this V, of course, is K minus V0 XYZ, plus a second derivative with respect to y of that same thing, plus a second derivative with respect to z of that same thing. So we differentiate the constant once, it goes away. We got a minus V0 XYZ. We differentiate that once, we get minus V0 YZ. We differentiate it again, we get 0. So we're going to get 0 from each of these terms because there's only a linear function in here, and when you take two derivatives of that, you get 0 back. So it does appear to satisfy Laplace's equation, which means it could be a valid voltage distribution. This isn't a foolproof way of testing that. In general, if you have a differential equation, you also have to have some boundary conditions, so this would also have to satisfy boundary conditions somewhere, but that's beyond the scope of this particular example. All right, so this is just an example. Something you should be able to do in class is to take a function and calculate its Laplacian by differentiating, and you could do that in any of these three coordinate systems here. Now, if we go back to the integral relationships we had here, we had the integral of E dot dl around a closed contour equal to 0, and the integral of d dot ds around a closed surface equal to q enclosed. And we'd like to ask the question of what happens if we're at some interface where we have two different materials. So we say we've got an epsilon 1 on this side, epsilon 2 on that side. The material changes, and we'd like to know something about what happens to the fields when the material changes like this. So in particular, we could take a contour here, and since this applies to any contour, let me define a contour that actually sort of hugs the interface here. So I'll define my contour C as one that runs up on the left side, runs down on the right side, and then jumps across. So part of the contour lies in region 1, and the other part lies in region 2. Okay. And if I take this integral of E dot dl and at least conceptually sort of apply it to this situation, then I get the following. And I'm going to neglect the short sides of this. I'm going to actually let the contour conceptually shrink down so it just hugs this interface, the left-hand path on one side, the right-hand path on the other side. So I've got the integral of E1 dot dl over, say, C1 plus the integral of E2 dot dl over, say, C2 here. Okay. And that basically gives me back something I'll call E1 tan times, say, delta L, maybe in the L hat direction for the left-hand integral. and on the other side I'll have an E2, tan denoting that it's tangential to the interface here. There's a delta L. Now we're coming back the other way, so this is really a minus L hat. So those are our two contributions there. And this says these things have to add up to 0. So this says that E1 tan times delta L minus E2 tan times delta L, all sort of dotted with L hat here. This is really a dot product, I guess. Has to add up to 0. Or that since L can be any tangential variable here, this really says that E1 tan has to be equal to E2 tan. So that says if this first equation is going to hold, then the tangential part of this field has to be continuous across that interface. Question?
Why do you write tan like that?
Why do I write it like that?
It's like it's superscript.
I just wrote it as a superscript. That's the way I always write it. I don't know if nothing special about it. It just denotes tangential. I mean, it's doesn't matter how you write it. I mean, you could write it, you know, E1 tan as a subscript if you want. But the point is, we're talking about just the tangential part of the field on the interface, not the part of the vector that might be normal to the interface here. Okay. Now, we can actually specialize this to two cases. The first case, say, is when region 2 is a conductor. Okay. Now, if region 2 is a conductor, what does that tell us about the field in region 2? What is the electric field in region 2 going to be if it's a conductor? It's going to be 0. Okay, so that means E2 is equal to 0. And if E2 is equal to 0, then the tangential part of that, E2 tan, is also going to be 0. Okay. And according to this equation, that means that E1 tan is going to be 0. There's a knob on the back of this chair here that keeps grabbing the microphone wire. So we conclude from this that E1 tangential is 0, or namely that the tangential field near the surface of a conductor has to go to 0. Okay. So that's one special case. Another special case is the case of two dielectrics, which is really what we started with here. And in that case, we basically have just what we started with, that the tangential component stays the same on both sides, but it's not necessarily going to be 0. Okay. Now, there's other ways of writing this, all right? Another way of writing this is to say that, all right, let's define a normal vector to the interface here, and I'll define it so it's pointing into region 1. Then another way of writing this is to say that n cross E1 minus E2, n cross E is basically, when you do a cross product, you lose the part of the vector that's parallel to n. You just get the part that's perpendicular to n. So n cross E1 is really another way of writing E1 tan, except it's been rotated 90 degrees around. All right. So in this case, since E tan is the difference between these etans is 0, we can write it as n cross E1 minus E2 is equal to 0. So for a conductor, that's the same as saying that n cross E1 has to be 0. Or n cross E just outside the conducting surface has to be 0. So that's the same as saying E1 tan has to be 0. Okay. This condition only holds right on the interface. So a more accurate way of writing this would be to say n cross E1 minus E2 right at the interface has to go to 0, or n cross E1 right at the interface has to equal 0 if it's a conductor. Okay. Now if we substitute in here and look at the electric flux, remember D is equal to epsilon E, so D1 would be epsilon 1 E1, D2 would be epsilon 2 E2, and in general here epsilon 1 and 2 are different. So if we make that substitution, then this says that n cross E1 is actually D1 divided by epsilon 1, and E2 becomes D2 divided by epsilon 2, and that says that n cross that difference has to be 0. Okay. Now since epsilon 1 and epsilon 2 are different, that says that the tangential component of the D field changes as we cross the interface. So D1 tan is not continuous in this case. Okay. So these tell us something about the tangential components of these fields. All right. If we wanted to look at the normal components of the fields, then we have to do something a little different. Let's go back over here and create a little box of some sort that sort of, again, hugs the interface here. Maybe I'll curve it around so it looks like a can of cat food or something here. And we want the top face of the can to be in region 1, the bottom face of the can to be in region 2. And now we're going to smash the can down so it just hugs this surface, basically, okay? And then we'll define our normal vector again to be pointing basically toward the region 1 side perpendicular to the surface. Okay. And now let's look at the second integral relation here, which is the integral form of Gauss's law, and apply that to this can of cat food. And we'll assume that there's some charge on this interface, and we're going to let the can shrink down, so any volume charge is going to get left outside the can eventually, but there might be a layer of surface charge density on this interface. Call that rho sub s. Okay. So if we do that, then this integral over the closed surface of d dot ds is basically going to collapse down to the integral over the face that's sitting on the region 1 side. Call that face 1, plus the face that's sitting on the region 2 side, face 2 of d dot ds. Okay. So this is approximately going to be the D field dotted with the normal vector times, say, the area, call that delta A, on face 1. This would be, of course, D1 and D2 now, since we're on these two different faces. And then by convention, when we're doing an integral over a closed surface, the normal vector always points out, so the ds vector back on side 2 is going to point in the minus n direction. So we'll have a minus sign in here. We'll have a d2 dot n delta A. So if we let this can shrink down to the interface and then let the area get small, this integral gives us approximately this. And if there's a surface charge density on here, then that stays inside as we shrink the can down. And we're going to capture exactly delta A of that. So there'll be a rho sub s delta A on the other side of that equation. So this is the Q enclosed in this case. So the surface area, rho sub s, so many coulombs per square meter, times so many square meters of area gives us total Q in coulombs. So what this says is that we basically have a normal component of the field here and here. If we divide through by delta A, this says that n dot d1 minus d2 is equal to rho sub s. Or you could write it as d1 normal. Really, d1 normal is a scalar. So I'll drop the vector sign, minus d2 normal equals rho sub s, or you could put the normal as a subscript if you want to do it that way. So that becomes the general condition. Now again, there's two special cases that come out of this. In the first case, region 2 is a conductor, and that means that E2 is 0 and D2 is 0, and therefore D2 normal is also 0. And then this equation simplifies down to n dot d1, again at the interface, equals rho sub s. Okay. Or since d is actually epsilon 1 e1, we could write this as n dot epsilon 1 e1 at the interface equals rho sub s. So that's the condition if we're dealing with a conductor. There's some surface charge on the interface, and we get this condition. The other special case is if regions 1 and 2 are both dielectric, and usually that implies that there's no surface charge on the interface. Okay. So then we're back to this condition here, but it has a 0 on the other side. So we could write it as n dot d1 minus d2 equals 0, or we could write it as d1 normal equals d2 normal. Or we could substitute epsilon e in for d and write it as n dot epsilon 1 e1 minus epsilon 2 e2 equals 0 on the interface, or epsilon 1 e1 normal equals epsilon 2 e2 normal on the interface. So all of these conditions apply just on the actual interface between the two regions. So earlier we derived this condition saying the tangential parts of E and D follow these rules. Now we've got conditions involving the normal components of E and D at an interface. Any questions about that? So these are what we call the boundary conditions that these fields have to satisfy at material interfaces. Often this becomes the boundary of the region we're working on or something here. They're also sometimes called continuity conditions, because what they're really telling us is how the field behaves as we cross the interface here. Okay. So to illustrate this, let's look at an example of what we can do with this. Suppose we've got two regions, and the regions are basically separated by the z equals 0 plane here. Okay, so this will be region 2, and this will be region 1. Region 2 will have a permittivity epsilon 2 equal 4 epsilon 0. Region 1 will have epsilon 1 equal 5 epsilon 0. So we've got two pieces of ceramic or something butted up against each other here at this interface. Okay. And now we're told that just to the right of the interface at z equals 0 plus, we somehow create a field through here in such a way that we've got E1 equal to, say, 2E0 x hat plus z hat. And we'd like to know what is E2 at z equals 0 minus, just to the other side of the interface. Okay, how should we proceed to answer that question? So we just talked about how the tangential parts of the field behave, how the normal parts of the field behave at this kind of interface. Now we're given a field. So the first step here is to try to figure out what is the tangential part of this field, what is the normal part. Okay, so what do you think? We've got an x component and a z component. Which of those is the tangential part? Or is the tangential part some combination? Okay, so this is the z equals 0 plane, right? So this is the z-axis running that way. Okay, so yeah, so the normal vector here, if we wrote down a normal vector pointing into region 1, that would be along z. Okay, so the z component here is the normal vector. The x component is running somewhere parallel to the plane here, so that's what we mean by tangential. So in this example, we can separate this into E1 tan equals 2 E0 x hat, and E1 normal equals 2 E0 z hat. Okay. All right. What's E2 tan going to be? E2 tan and E1 tan have to be the same at the interface, right? So this is going to be equal to E2 tan. What's E2 normal going to be? That's a little more complicated. E2 normal is going to be epsilon 1 E1 normal over epsilon 2. Okay. So E1 normal is this. E2 normal is going to be epsilon 1 over epsilon 2 E1 normal. Okay. So this is going to be 2 epsilon 0, 2, this is 2 E0, epsilon 1 is 5, epsilon 0, epsilon 2 is 4, so we got a 5, 4 in here times 2e0 times z hat. Okay. And my total E2 is going to be what? The sum of these, right? So that's E2 tangential plus E2 normal. So we're going to have a 2E0 here times a x hat plus 5/4 z hat. So if we have this field just to the right of the interface, then we have to have this field just to the left of the interface in order to satisfy these continuity conditions. Okay, so this is a conceptual way to do this, where you sort of systematically break up the field into its tangential part and its normal part. Another way of doing this would be to just say, all right, let's assume that E2 tan and E2 normal, we can just put them all together and say E2 is given by, say, alpha x hat plus beta y hat plus gamma z hat. Introduce three unknowns into the problem, and then apply the various conditions. So one of the conditions is that n cross E1 minus E2 has to equal 0 at the interface. That's n cross. We've got an alpha x hat from E1, or we've got a 2 E0 x hat from E1 minus alpha. So we'd have a 2E0 minus alpha x hat. We'd have a 0 minus beta y hat. We'd have a 2E0 minus gamma z hat. And then cross all of that has to equal 0. And we figure out what the normal vector is. That's going to be z hat. We work out the cross products, and we get two equations out of here that we can solve for two of these three unknowns. Then we go to the other condition over there that says n dot epsilon 1 E1 minus epsilon 2 E2 equals 0. Substitute in E1 and E2. That'll give us one equation. So we wind up with three equations, three unknowns, and we can solve those for these unknown parameters, alpha, beta, gamma, and work it that way. So that's just straight math, crunching through a bunch of equations with these conditions, but that's a valid way to work the problem too. So this is more of a conceptual way to work the problem. What is the tangential part? What is the normal part? This is just crunching through, solving a bunch of equations and unknowns. Okay, so that's an example involving two dielectric regions. Let's look at another example involving a conductor. And in this case, let's let the region xy less than 1 be a conductor, and let's suppose it has a surface charge density on it, rho sub s equal to 4 epsilon 0, and we'd like to find the electric field just outside the surface. Assuming that we just have free space out there. Okay, so if we sketch this out, this is really just sitting here in the two-dimensional plane. xy less than 1 is I guess a parabola of some sort here. Looks like that. So this is our conductor to the left of that. And we've got some surface charge sitting on here, and that's going to produce an electric field of some sort out here in the air region. So this is epsilon 0 floating around outside there. All right, so in this case you've got to figure out what the normal vector is, so you can play around with the math here a little bit. Figure out from this equation, basically the boundary here is xy equal 1. A good exercise is to figure out what the tangent vector and normal vector would be to that particular surface. In this case, what you wind up with is a normal vector that's xx hat plus y hat divided by square root of x squared plus y squared. So that's our normal vector to that surface everywhere. And in this case, we're dealing with a conductor. We know that E is 0 in the conductor. So what is E tan going to be just outside the conductor? 0. So that says if we have a non-zero E out here, it has no tangential part, it's entirely normal. So we only have to really worry about the normal component. And the normal component then, since we're by a conductor, we would use this equation here that says n dot epsilon E is equal to rho sub s. Okay. So in this case, we've got an E field that's pointing in the normal direction. Okay. That E in the normal direction is going to satisfy n dot epsilon 0 E equal rho sub s. So that tells us that the magnitude of E normal is rho sub s over epsilon, and it's pointing in the n direction. Okay, so in this case that's 4 epsilon 0 over epsilon 0 xx hat plus y hat over square root x squared plus y squared. Question?
So, like, how did you get the x hat plus y hat over the square over there?
All right, well, that's geometry. There's probably several different ways you could do it. If we just look at the equation xy equal 1, all right, obviously it's harder to find a normal vector than it is to find a tangent vector. So let's just say first we wanted to find a tangent vector. A good tangent vector is the differential length vector dl, which would be dx x hat plus dy y hat. And all we need is a relationship between dx and dy, which we can extract from this equation here, for instance. So from that equation, we can say, well, you've got, differentiate this equation, you've got x dy plus y dx equals 0 from that. So that says that dy is going to be y over x, or minus y over x dx. Okay, so we substitute that in for the dy in here. So this becomes dx x hat minus y over x dx y hat. So that says if we change the length of this, there's some tangent vector. If I just drop the dx here, that's given by x minus y over x, x hat minus y over x y hat. Okay. Now that's a vector. I can look at this and tell kind of how this works as we run off to the right on the curve here. That y is going to 0. my vector's going to x hat, so clearly the t that I've chosen here is pointing that way. Okay. Now I want to rotate this around and get a normal vector. One way of doing that is to take z hat, which is out of the board, cross it with t to get n. Okay, so n in this case would be z hat cross t. Z cross x is y, so this is y hat. Z cross y is minus x, so this becomes a plus y over x, x hat. Okay, and now I want to make that a unit vector. When I make it a unit vector, I calculate the length of this. The length of this is 1 plus y over x squared, square root of that. So I divide by that, and then if I multiply through by x, I get this. So this is math. It's a good exercise to sometimes play around and review these things because, this is a sort of back-of-the-envelope calculation that can really bog you down if you don't have any way of whipping that off. But finding the tangent vector, knowing that you can start with this dl vector and working that out, I found that to be a fairly useful thing to keep in the back of your mind somewhere, how to do that, and then you can play around with vectors and so on, figure out how to write these things down. So if we're dealing with conductors, the key idea here is that the field just outside a conductor is entirely normal. So if you know the normal vector, you know the direction of the field, and its magnitude is going to be rho sub s over epsilon. So that gives you the normal component of the field, and if it's adjacent to a conductor, it's the whole component of the field. Okay, any questions about that? All right, so these are some things you can do with electromagnetic boundary conditions. So these will pop up from time to time. These involve just the electric field. Later on in the course, you'll study the magnetic field and look at the boundary conditions associated with those fields as well. It's a similar kind of derivation, and you can use them in a similar way. Okay. All right, so you have this force field. So you've got some charge distribution, and along with that you've got some voltage, and you've got some electric field, and there's various ways of working with this stuff. So this is a physical force field around charge. You know, if you had a group of charge here and you brought some other charge over and let go of it, there'd be a force on it. It would either be attracted or repelled by this charge distribution. So we take that force field and we can call it an electric field, we can call it a voltage potential function, we can call it whatever we want, but there is some physical field around here, some kind of force field, and these are just different labels we've made up to put on that field. Okay. Most of the time, when we talk about electromagnetic fields, we think of these vector fields. But when we're working with vector fields, you have more stuff to keep track of. You have to keep track of the vector direction as well as the function of position. So usually if you can work with a scalar field instead, that makes it easier. So that's really why a lot of times we'll work with this scalar potential or voltage instead of working directly with the electric field. Okay. Now, in a lot of situations, when we have to work with voltage, it basically comes down to going back now to Laplace's equation. And we basically want to just solve Laplace's equation to try to solve these problems. Okay, so often we need to solve Laplace's equation. So this is a partial differential equation, second order. We also have to have some boundary conditions to get a unique solution out of that. This is something where there's various techniques. that you've studied in your differential equation class, where you can try to apply and bring to bear here. There's one technique called separation of variables that works if you're in if you're dealing with a problem where all the boundaries coincide with constant coordinate planes in Cartesian, cylindrical, spherical. It becomes very easy to come up with general solutions to Laplace's equation. In a lot of practical situations, you don't quite have that, and therefore it becomes much harder to try to come up with exact analytical techniques for solving Laplace's equation. So there are, exact mathematical ways of doing this. There's also various approximate ways of doing this. And nowadays, approximate means kind of numerical. So if we look a little bit at trying to solve Laplace's equation using numerical techniques, it turns out Laplace's equation is rather nice in that regard. And one of the simplest numerical techniques we can use is known as the method of finite differences. Okay, so if we just do this in 2D, say, in the xy plane to illustrate this, then Laplace's equation becomes second derivative of v with respect to x plus second derivative of v with respect to y equals 0. And it's equal to 0 in some region, and we have to augment that with boundary conditions where we either specify v on the boundary, where we have to specify the derivative of v on the boundary, or something like that in an actual problem. So specifying v on the boundary in an electric field problem is like specifying the voltage there. So if you're analyzing a capacitor or something, you normally have two plates. You put a voltage on each plate, and you want to know what are the fields doing between those plates. Okay, I think that's a problem you'll get to maybe on Wednesday this week. If you're specifying the derivative of v on the boundary, then you're specifying the E field there, or one component of the E field there. So you can mix those things. You can specify v on part of the boundary, the E field on part of the boundary, or so on. And in principle, if you have that information all the way around the boundary, you should be able to solve this equation. Okay. Well, doing this with finite differencing usually suggests that you're going to stick with a regular Cartesian mesh. So you've got some kind of coordinate system here where you've got x and y, and you take this two-dimensional region and you basically define a bunch of points throughout that region where the voltage is going to live, so to speak. So you're going to work with this discrete space instead of a continuous space. You're going to work with the voltage here, 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 and so on. Okay. Now, what this differential operator says is, well, dv dx squared plus second derivative of v with respect to y squared, we need to approximate those derivatives based on this kind of grid. Okay, so let's say we had equal spacing throughout the grid here, where we had delta x is the spacing between grid points along the x-axis, delta y as the spacing along the y-axis. Then, of course, your derivative here, dv dx, would be approximately, let's call this, well, you follow the notation here. Let's say we were working at a point here. Let's call this v north, v south, v west, and v east, as though we were looking down on a map or something. And just leave this as v for v in the center. So if we want to calculate derivatives on here, dv dx might be, well, that might be v east minus v divided by delta x. So that's what we mean by a finite difference. It's just a difference there divided by delta x, and the limit as delta x goes to 0, this becomes the actual derivative. Here we're not going to take the limit, we're going to let delta x be some size, but if we want a better answer, we might make these points closer together and essentially take some kind of limiting process that way. Okay. If we wanted dv dx to the left, that might be vw, or it's v minus vw over delta x. Okay. Now, strictly speaking, if we take the derivatives this way, what we're really doing is we're defining them, say, halfway between these. So this would be dv dx at, say, a half here. And over here, we'd be getting dv dx at minus a half. If our ultimate goal is to get the second derivative, d squared v dx squared, right at the center point, then that looks like we've got dv dx to the right, dv dx to the left. We can take the difference of those two. So we take dv dx to the right minus dv dx to the left, and then divide that by this distance here from midpoint to midpoint, which is also delta x. So that then gives us a second order derivative, which is going to be v e minus 2v plus vw over delta x squared. Okay. And if we did the same thing running in the y direction, we'd get a second derivative of v with respect to y at this center point that would look like v north minus 2v center plus v south divided by delta y squared. Okay. So in general, we could work our finite differencing out using these equations. So instead of solving the continuous problem now, we basically define a grid of points like this, and our Laplacian d squared v dx squared plus d squared v dy squared becomes approximately the sum of these two things. So it's going to be VE minus 2V center plus VW divided by delta x squared plus V north minus 2V plus V south divided by delta y squared. And if this is really Laplace's equation, then we're setting that equal to 0. Okay. So if we have a big grid of points, say we had 100 points in our grid, we could write down one equation like this at every interior point. Let's say there were 100 interior points, and then we had some other points that were on the boundary. When we come to a boundary, then some of these values are known. And we can plug in the known values. When we're away from a boundary, we just have one equation involving 5 of the unknown quantities here. So this becomes a big system of equations. If we have 100 interior points, we have 100 equations involving 100 different unknowns. And that's a little tedious to work out with pencil and paper, but it's easy to program up and let a computer work out. And the idea is to let a computer actually solve that system of equations for you. Okay. Now, it gets a little simpler if delta x is equal to delta y, because then we can combine these denominators together. Then we get VE plus VW plus VN plus VS minus 4V all over delta squared is equal to 0. And we can just drop the denominator out of there, and we're left with this equation. And you can see what that equation is doing is basically forcing the voltage in the center to be the average of the 4 voltages around it. Okay, so this forces the voltage So you can take a problem that you want to solve and assign some boundary conditions to it and so on, and a grid of points, and you can work through this kind of thing either by hand, or you can write a computer program to do it in MATLAB or something like that. You can even do it on a spreadsheet, because you've got an equal cell kind of thing. So you can open up like an Excel spreadsheet and write an equation that basically says the value of the voltage in this cell is the average of the 4 around it. You can copy that equation all over the place, put in hard numbers around the boundaries somewhere, and then the spreadsheet will just iterate until this converges to the final values. Okay, so that's an easy way to do it if you're sticking with rectangular boundaries or something. All right, and of course the effect of this is to kind of average things out. So let's say you let V equal 0 on these two walls, and you set V equal 10 up here, and maybe V equal 5 or something on this wall. Well, when you get done, and then you put a bunch of grid points in here, you know, you're going to get something where up here your values are at 10. They're going to, you know, very sort of rapidly drop off as you come over here to this boundary. So they're going to go to 0, you know, 2, 4, 6, 8, 10 along some curves. Over here they're going to drop to some value like 5, and then they're going to, you know, there's probably going to be some, you know, some curves in here where they drop. So you're going to see a final answer that's a transition like this. Okay, so the net effect of this is that the voltage at any of these nodes in here is going to eventually become the average of the 4 around it, which is a fairly simple process. So you can, you know, work this out. It may take a little while. If you actually built something like this and held the voltages like this, Mother Nature would solve the problem instantly and give you those values back too. Okay. So let's look at a simpler example here where we just have a few unknowns. Let's say we had a grid of points. We'll take a 5 by 5 lattice here. And I'm going to set the ones on top to be 100 volts and set the ones around the sides to be 0. And now we want to know how this process is going to work. Okay. Well, it just so happens that this is one of these numerical techniques that's always guaranteed to converge. Okay, there are techniques that go unstable and so on, but when you're solving Laplace's equation like this for these kind of boundary conditions, it always converges to the answer, doesn't oscillate or go unstable or anything. But if you were doing this by hand, you would go through, and at every node you would take the average of the other nodes. So you'd make an initial guess, maybe set all of these things to 0, and now go through and start averaging. So if we start at this node, I'm going to average these 4 nodes. That's going to bump that up to 25. All right, if I go to this node, average these 4 nodes, now I'm going to be 125 divided by 4. That's, what is that, 32 or something? 32.25 or something like that. I go over here, I get something that's a little bigger than that. Let me see, maybe he's got the answers here. Okay, I guess he's not even doing it. He's going through and doing it all in one pass. So the next pass, we still treat this as 0. You get 25, 25, and so on. So the first iteration, it converges to something like this. You go back through another time, and on the second pass now, we get 32.25 here. This next one goes up to 37.5. This one goes to 32.25. And so on. You go to the next row now, and these all go to 6 1/4. And you keep doing this, okay? You make a third pass. On your next pass, the numbers change. You get 35.94, 42.69, 35.94, 9.63, 12.5, 9.63, 1.56, 1.56, 1.56. And you iterate a few more times, and the values pretty much start to converge to their final answers here. Okay, so this is an example of a simple numerical technique, but it's one that you can work out almost on the back of an envelope, and it does give you some idea, a pretty good idea at least, of how a voltage distribution is going to spread around. So there's problems where you might want to estimate the capacitance of something. You could solve Laplace's equation with some simple boundary conditions and get a pretty good insight into what that capacitance is going to be, for instance. So again, you'll talk about capacitance problems, I guess, Thursday this week. Now, there are obviously more sophisticated kinds of numerical techniques you can use, and we're not going to go into much detail about those here. But if you're interested in numerical techniques, there's actually a nice website that compiles a whole bunch of different techniques for a lot of different problems in electromagnetics. And this is at the Missouri Institute of Science and Technology. The website is emclab.mst.edu, and there's a page for commercial software, CSoft. Some of this is commercial companies. There's probably a list on here of 40 or 50 different software packages from different places. Some of them are free, some of them you have to buy. But there are a number of these that work for electrostatics problems, capacitance problems, and various other things. So this is kind of a nice something to keep in the back, reference to somewhere. If you're ever looking for commercial software, this gives you a place to look where they kind of lay out a lot of the software you can use to solve electromagnetics problems on this site. But this is probably the simplest technique for solving an electromagnetics problem numerically by using this 5-point finite difference operator. Okay, I will stop there. Are there any questions? And as far as I know, Professor Durgan will be back on Thursday.